So yeah, that's the P set. And yeah, so today we'll be doing the correspondence theorem. You did the problem too without assuming the proposition? That's interesting. I think we did see your solution, did we? Can't remember, but yeah, most of the people did that with the proposition, using the proposition. Yeah. But yeah, we spent actually a lot of our time with the last Bourbakis problem, and I don't think I haven't tried it. I didn't get the time to, but JP had the only solution which actually worked. So yeah. Anyways. So, does anyone have anything to say about today's sections? Anything that you want to skip right away, or anything that you want to focus on? I think correspondence theorem, most of it is non-trivial, but
really had to get out pencil and paper and work through that example they had about mapping from S4 to S3. Just as an example of the correspondence theorem. It was a great example, but definitely not something I could just skim through without putting pencil to paper.
Okay, that's interesting. Let's see. The example you're talking about, that is 2.10.6, right?
Yeah, that was the one.
Okay. So let's see. We have the correspondence theorem, and okay, so we're going to finish Artin today. So let's see. So you have a group homomorphism, and you have a subgroup of G. So here you have the group homomorphism going from G to curly G, whatever, and H is a subgroup of the G, right? So what you do is you restrict phi, the homomorphism, to H, and then you get a restricted homomorphism, which is going from H to the curly G, right? So it's similar when you actually restrict a map to a subset of itself. But so here the homomorphism doesn't lose its properties; it's just restricted. It has been restricted to a subset of its domain, right? So by definition, if H is in the subgroup, then the restricted phi of H is going to give you phi of H, of course. So if you want to check like if the restriction is actually well-defined homomorphism, it is not really something hard to see, because phi is a homomorphism. So if you restrict it to a subset, and like it's not really a subset, it's a subgroup, so it has all the properties from G. So if you have a homomorphism from G, it works well with its subgroups. And the kernel of this restricted homomorphism is equal to the kernel of the original homomorphism intersection the subgroup, right? And that makes sense, because of course the image of the restricted homomorphism is going to be the same as phi of h under the original map, right? Okay. So we have some examples. This example is that the image of the sign homomorphism sigma, taken from the nth symmetric group to the plus minus 1, has order 2. The image of this homomorphism is just plus minus 1, thus has order 2. If a subgroup H of the symmetric group has odd order, it has the order is odd, it will be contained in the kernel of the homomorphism, that is the alternating group, right? We've seen this before, how the kernel of the symmetric group is the an of but this time it will be contained in the kernel of sigma, that is the alternating group of even permutations, right? Okay, so this will be so when H is actually the cyclic subgroup, so it can't really be any subgroup, it has to be the cyclic subgroup generated by a permutation Q that is an element of odd order in the group, right? So this H is the cyclic subgroup which is generated by a permutation. So Q is a permutation in Sn, and it has an odd order in the group, right? So every permutation whose order in the group is odd, such as n cycle with n odd, is an even permutation, and that makes sense. Thus, a permutation that has even order in the group can be odd or even. So it depends upon it doesn't really matter if it's like a permutation that is an element of the symmetric group whose order, that is the cyclic subgroup that it generates, has an order that is odd. It can be it is an even permutation, right? So thus if you have an even order, its its permutation can be odd or even. So you have to really make sense here, because they're talking about odd and even permutations and odd and even order, right? So if something has odd order, then it is an even permutation. But if something has even order, then it can be either an odd or even permutation, right? Okay. So if you take the determinant, as we've seen before, the function, the homomorphism going from GLNR to the general linear group to the real number to the multiplication, what you do is the set of positive real numbers is going to be a subgroup of this R cross, right? And wait. And they say that this set of positive real numbers is actually normal with respect to R cross, because R cross is abelian. Yeah, you have commutative property and under the multiplication of real numbers, right? So its inverse image, the set of invertible matrices. So if you take the inverse image of these positive real numbers, so they're going to be the wait. Wait, can you hear me?
Can now.
Good lord. Today is a terrible
Yeah,
day.
just now.
Yeah. So, my bandwidth is terrible. Let's see. If I don't stream, can you guys like follow along with the book?
I have the book handy.
Okay. I mean, I can record, but like streaming seems impossible as of now. Let me try. Okay, so if this works, at least for the time being, um, let's see. Can you see my screen? I guess you can.
Cannot.
You cannot?
I can. I can.
Okay.
Go out and back in. I can see
Okay.
it now.
Okay. So, what is that? We have the following proposition after the example, right? Which says that if you have a homomorphism and you have the kernel K and you have this curly H is a subgroup of this curly G, um, then you denote the inverse image, the pre-image of this curly H by this H, right? So this H is a subgroup of G, right? So that's the domain that contains the kernel. So now if H is a normal subgroup of the curly G, then this H is a normal subgroup of the domain G. Right? So if phi is surjective and if H is a normal subgroup of G, then that's also a subgroup. So your normal condition smoothly transfers along with the homomorphism over the two groups and their subgroups, right? And there is a problem relating to this about the normal subgroups and the homomorphism in the P set. That is slightly a tricky one. Okay, so for example, wait, oh, did we actually cover this? And I just said it again. Anyways, so we have to prove this proposition, and the proposition is one. So the proof is that the pre-image is not a map. The pre-image is just a set in the domain G. So by definition, the pre-image of H, the curly H, is the H. It's a set of elements such that those elements get mapped to the curly G, curly H. Wait, yeah, H is the set of elements x of G such that phi of x is an H. Yeah. First, if x is in the kernel, then the image is just the identity. Since one is included in the subgroup curly H, X is also in there, thus H must contain the kernel. Then you have to just prove that it is actually a subgroup. So you have to prove it being closure, which it is due to phi being a homomorphism. Then you have to show that there's an identity, which there is. The inverses are also similar. So you have to also show that if the curly H is a normal subgroup, then the H in G is also a normal subgroup, and that's also like pretty much straightforward. If the curly H is a normal subgroup, you have the conjugates in there, then you can transfer the conjugates with the help of the homomorphism into the H, and you'll have the conjugates there, thus making it normal. Right. Yeah, so the proof is pretty much straightforward, but the proposition is kind of important. So if you have a homomorphism and you have the normal subgroups, they work nicely. Okay, so correspondence theorem. So the correspondence theorem says that you have this surjective group homomorphism, as we saw before, and has the kernel K. So it says that there is a bijective correspondence between subgroups of the curly G and the subgroups of G that contain the kernel, right? So it's somewhat related to the proposition, but not entirely equivalent, right? So if you have such a group homomorphism, then there is a one-to-one correspondence between subgroups of the codomain and the subgroups of the domain that contain the kernel, right? And this correspondence is defined as follows. So how the correspondence works is a subgroup H of G that contains K gets mapped to its image phi of H in the codomain. So and a subgroup H, the curly H of the codomain gets mapped to its preimage in the G. So there is a one-to-one correspondence between these subgroups that contain the kernel and the other subgroups of the domain. Right. Okay. So if H and the curly H are corresponding subgroups, then H is normal in the domain G, right? If and only if the curly H is normal in the curly G as well, right? So if you have a correspondence between two H's, then the normal H, not the curly one, the normal H is a normal subgroup in G, if and only if the other one is normal in the curly G, right? The notation is a bit weird. I've seen better notation in other books, but yeah. If H and curly H are corresponding subgroups, if they have a correspondence, then the order of H is equal to the order of curly H times the order of the kernel, right? So that makes sense. Okay, so we have the example 2.10.6. So the example that you have is you have the phi homomorphism going from S4 to S3. That was defined in example 2.5.3, and it's a kernel. So let me just quickly glance what was 2.5.3. So, 13, sorry. Wait. The example that was defined for this phi was that it takes, okay, so it defines the map phi from S4 to the group of permutations of the set with the partitions. That right? You had the partitions pi 1, pi 2, and pi 3. So you were mapping to the group of permutations of that set of partitions, and that would be the symmetry group of 3 elements. So three items. The group S3 has 6 subgroups. 4 of them are proper subgroups. Okay. Then with the usual presentation, there is one proper subgroup of order 3, the cyclic subgroup X, and there are 3 subgroups of order 2, including Y. Alright. Group S3 has 6 subgroups, that's clear. There is one proper subgroup of order 3, the cyclic subgroup of X. And there are 3 subgroups.
This was the cycle 1, 2, 3.
Yeah, right. So there are 3 subgroups of order 2, so that would be your transpositions, right?
Right. Yep.
Including the Y cyclic subgroup, because Y square is 1. Yeah. So okay, that's clear. So the correspondence theorem tells us that there are 4 proper subgroups of S4 that contain the kernel K. Right? The kernel K consists of the identity and the products of disjoint transpositions. So that would be 1, then 1, 2, 3, 4. So 1, 2 transposition, then multiply it 3, 4, then 1, 3, 2, 4, 1, 1, 4, 2, 3. So it's the product of disjoint transpositions. So the correspondence theorem tells us that there are 4 proper subgroups that could contain the kernel, right? Since you have 4 elements in the kernel, right?
Since there were four proper subgroups of S3. For each subgroup, each proper subgroup of S3, we get a proper subgroup of S4 that contains the kernel.
Yeah, that's from the theorem. Right. So, and then from the the other part of the theorem, it says that because the kernel's order is 4, there is one subgroup of order 12, and there are 3 of order 8. Because so yeah, because you have one proper subgroup of S3 that has order 3. So from this theorem, from this formula that you have right here, you're going to get one subgroup that has order 12, that will be 3 multiplied 4. Then the other 3 are going to be 2 times 4, right? Because you have 3 subgroups of order 2. So you will have 3 of order 8. Okay. Yeah, and like one of these subgroups of order 12 is going to be the A4 alternating group of 4 4 elements, right? So this is the subgroup that corresponds to the cyclic group X of S3, right? Because it has wait. Right, because it's going to contain the kernel, and you correspond that to the subgroup of order 3, and that is the cyclic group generated by X of S2. Okay. Then the subgroups of order 8 can be explained in terms of symmetries of a square. Okay, let's see. So you label the vertices of a square in this manner, and wait. It's a mess. I don't think I can stream, so we'll continue with the audio, and hopefully that doesn't make any mess. So the bandwidth is really bad today for some reason. Yeah. Okay, so we have the square containing these 4 labels at the vertices. So if you like have a counterclockwise rotation to like 90 degrees, then you would have like the cycle 1, 2, 3, 4. right? So you start from one, go to the left, and then have a counterclockwise rotation, making the 4 cycle. Then if you like exchange the diagonal vertices, you're going to have a transposition. So you're going to cycle between two numbers, two elements. So these two permutations generate a subgroup of order 8, alright? So right.
So when I was reading this yesterday, what I had to pencil to paper to figure out was that subgroup of order 8 actually does contain kernel of the mapping to figure out what element of S3 corresponded to. And you guys can just look at it and see you're doing better than I did. I had to write the permutations down and figure it out. Works. Just it didn't seem obvious to me.
Wait, so you're saying like this subgroup of order 8 contains kernel? Okay, it does. So the kernel has the transpositions and the products. Wait.
What he's implying without working out the details is that subgroup of order 8 of S4 corresponds to those subgroups of order 2 S3. So it corresponds to transposition in S3. The identity together with a transposition.
Okay, yeah, does make sense. Though I'm not sure if I get the intuition right. Okay. I'm not sure if I have a better way to explain this, but yeah. Okay, so we have the proof of the correspondence theorem, and the proof has a few things in it before we get to products. But I think like I need to do a few problems on these permutations. I'm not sure if I'm clear on most of these things. And unfortunately I don't think I put any problem regarding these permutations in the preset either. So yeah. Okay, so the proof says something like this. You have a subgroup that contains the kernel and the other curly subgroup in curly G. So you have to check the following things: that the image of H is a subgroup of the codomain. Then the preimage of G is a subgroup. So preimage of curly H is a subgroup of G and it contains the kernel. Then H is a normal subgroup if and only if its preimage is a normal subgroup. Then you have to check the bijective correspondence. Then you have to check that the order of the preimage is equal to the order of the group subgroup times the order of the kernel. Okay, so phi of H and so the preimage proposition and the normal subgroup thing is something that we've just proved before, right? Because we know that the restricted homomorphism, the image of the restricted homomorphism is a subgroup. Okay, so the bijective correspondence, you have to right, so you have to like take the images and then their preimages and see if they're consistently a one-to-one. Okay, so phi of the image of the preimage of this set curly H. So here you're just taking any subset that's going to just give you the same thing, right? Here you just consider like a map between sets, that is S to S prime, and H is a subset of S prime. Also, this H is a subset of the pre-image of the image of H, right? So H, the normal H, which is going to be in S, yeah, that's going to be the pre-image of the image of H. So yeah, that makes sense. And this is true for any map of phi of sets and any subset H of S. Okay. Then the only thing remaining to be verified is that H again is a subset of the in the other way. So if that happens, you're going to have the desired equality, right, for the bijective correspondence. So to show that H is again a subset of this pre-image of the image of H, then you take an element of this phi pre-image of the image of H. You have to show that X is in H too. Right? But like if X is an element of this, then phi of X is going to be in phi of H by definition of the preimage. But if let's say if phi of X is equal to phi of A, some element A in H, then the inverse of Ax is in the kernel, right? Because H contains the kernel. But since both A and A inverse X are in H, X is also going to be in H. And the last one is an exercise. This is the last one. The last one is actually straightforward from the counting formula and the counting formula regarding the kernels. So okay, so that was the correspondence theorem. Okay. I'm kind of still skeptical about that S4 to S3 thing. I think I'll have to recheck that, but yeah. Yeah, the partitions are labeled. I mean, the notation in general is not that elegant, but well, at least it is elegant, more elegant than Bourbaki. So. Okay, so product groups. We're going to see a few things about product groups. Then quotient groups. Okay, so you have two groups, G and G prime. The product set G cross G prime is going to be the set of ordered pairs with the respective elements on the respective groups, and this set of pair elements with this product set can be made into a group by component-wise multiplication, right? So you have this multiplication rule defined. That is, if you have an ordered pair A prime and you have another ordered pair B prime, and that results in AB, comma A prime B prime. Right? So that is how you define a product of two groups. And the identity is just the ordered pair of the two identities. The inverse is the ordered pair of the inverses. And the associativity law follows directly because you have the associativity of the two elements from the two groups. Yeah, so you can have this relation between these groups and their factors using something like the projections. But here the projections of course are going to be homomorphism. So you have G cross G prime, and then you have the I and I prime, which include G and G prime into the product, and you have the P for projection again, which take you from the product to G and G prime, right? So what the I is defined as I of X, where X is some element in G that maps you to X, comma the identity, right, in the product. And similarly, I prime of X prime will map you to 1, comma X prime, right? And the projection does the same thing, except instead of like giving you an ordered pair, it pulls out one of the components of the ordered pair and gives you the element of the group, respective groups. So these are the injective homomorphisms, and the projections are also homomorphisms. They are subjective, of course. Okay. And yeah, it's also not hard to see that the kernel of these projections is going to be the kernel of P is going to be 1 cross G prime, because of course your whole image is like you're getting the group other than the G prime, right? So you have the 1 cross G prime. So every element, the ordered pair is going to be all the elements from G prime ordered pair with the identity. Similarly, for P prime, the kernel is G cross the identity. Okay, so what you can do is you can like try to decompose given group as a product, right? So you have like let's say not really subgroups, but some other groups H and H prime, such that G is going to be similar to the product of H and H prime, right? Okay, so you have some examples of this. The cyclic group of order 6 can be decomposed, right? So cyclic group of C6 of order 6 is isomorphic to C2 cross C3. Cyclic groups of order 2 and 3. So how you see this is you have C2 as the cyclic group generated by Y, C3 is generated by Z. So Y squared is 1 and Z cubed is the identity 1. So what you do is you denote X, and that X denote the element YZ of the product group C2 cross C3. So you have the Cartesian product or whatever, the product of groups C2, C3, that you take the elements Y and Z, right? And you don't denote this order pair with X. So what you now have to do is you have to find the smallest positive integer k such that when you take the power of this x, it gives you the identity, right? So taking the power of x means taking the power of this order pair, so that would be y to the k, z to the k, and that will give you the order pair 1, 1. That is the identity, right? So the smallest positive integer which does that is k equals to 6, right? So okay, see ya. Okay, so yeah, I'm not too sure about the recording though. It has some issues. Maybe I'll take the time to edit and then send it. But yeah, because of this bandwidth issues, it got messed up. Anyways, so this X has order 6. But since C2 cross C3 also has order 6, it has to be equal to the cyclic group generated by X, right? And the powers of X are going to be like this. So you'll have the identity at some point, right? So that will be X to the 6. Wait, yeah. Yeah. So x to the 1 is going to be yz. X to the 2 is going to be 1 z square, because y square is 1. Then x cubed is going to be y cubed, and y cubed is just y. and Z cubed is the identity. Similarly, others. So that's the cyclic group of order 6. But this can get a bit more general. So, generally speaking, if you have two relatively prime integers, so right here you had 2 and 3, and they're co-prime, and their GCD is 1. So, if R and S are relatively prime integers, a cyclic group of order RS, that is the product, is isomorphic to the product of the two groups of their respective orders. So CR and CS. Yeah, and of course, if you do not have the like co-prime powers, then it's not going to work. So C4 does not equal to the product of C2 cross C2. Right? Okay. So yeah, we have this following proposition. A few things in there to prove. Then we have a proposition regarding the Klein for group. Let's see. Okay, so you have H and K as subgroups of a group. Then you have a map which takes you from H cross K to G, and it's the multiplication map. So it takes two elements from the subgroups and multiplies them in the group G, right? So its image is going to be in the set HK. So HK is going to be all the elements from H and K with their products, right? So yeah, its image is going to be the set of all the products of these elements from the subgroups. The propositions are is that F is going to be injective if and only if the only thing common between the subgroups is the identity, right? So what that means is that if they have something else in common, it cannot be injective, right? So okay, so then F is a homomorphism from the product group H cross K to G, if and only if elements of K commute with elements of H, right? So okay, so F is a homomorphism if and only if the elements from the subgroups commute with each other, right? Now if you have like one of these subgroups as normal, so if H is a normal subgroup, then HK, the image, is also going to be a normal subgroup of G. Okay. Then if F is an isomorphism from the product group, if and only if it is injective, that is, the only thing in common they have is the identity, then the image is the entire group G, and H and K are normal under G. Right? So that's when it's an isomorphism. Let's see the proofs. So if H intersection K contains some non-trivial element, that is an element that is not equal to the identity, then its inverse is also going to be in H. So f of when you apply this f to this inverse and x, it's going to be the identity. So that is equal to f of 1, 1. Thus, it's like it's not injective because you can show like one element which is mapped by two things in the pre-image, right? So that is two outer pairs get mapped to the identity, and that is not injective. So if you assume that H and K only have the identity in common, then we have two outer pairs from the product, and H1 K1 is equal to H2 K2, so the products are equal. Then we multiply both sides by the inverse of H1 and the inverse of K2. So So what you would get is K1 times K2 inverse, and that is equal to H1 inverse times H2. K1 times K2 inverse is going to be an element of K, right? Because K1 and K2 are elements of K, so the product of them is going to be in K, right? And H1 inverse times H2 is also going to be in H. But since H and K just have one in common, like this equality must be the identity, right? So if these two are in H and K, then their product has to be the identity. So if that is the identity, then you can say that K1 is equal to K2, then H1 is equal to H2 by the cancellation law. And thus the ordered pairs are the same, making the condition that they have the identity is the only thing common if and only if the map is injective. Okay, so B is pretty straightforward. So B says that the homomorphism is possible if and only if the elements of the subgroups are commutative. So you take two ordered pairs of the group again, of the product group, then the product of these elements in the product group H cross K is H1, H2, comma K1, K2, right? So that's the product. Now if you map this product, you're going to get H1, H2 times K1, K2. But the product of two of these images, right? So if you multiply f of H1 K1 with f of H2 K2, so you apply the function on two of these elements and then take the product, you're going to also get the same. You're going to get h1 k1 h2 k2, and like these things, h1 k1 and h1 h2, these two elements are going to be equal when these middle terms, right, the middle elements h2 k1 and k1 h2, if these two things are equal, right? So if these two things are equal, you can say that the products are equal, right? Thus making the case that there has to be commutativity, right? Because if you make these two equal, these middle two things, then that is just commutativity. Now C. Okay, so now if you have the normal subgroup H, now KH is right, it's going to be the union of left cosets, that is K capital H, and right, but right, so KH can be written as the union of left cosets of K and the subgroup H, and HK can be equally written as a union of right cosets HK, right? But since H is normal, your left and right cosets are the same, so KH is equal to HK, so therefore HK is equal to KH in the sense of in the sense that they are the same thing, right? So it doesn't really matter where you multiply K and H. So the closure of HK under multiplication follows because right, HK is going to be equal to HHKK. This is because we just show that they're commutative. So commutative in the sense that they're the same set. So HK is equal to KH. So it doesn't really matter if we do that twice. So now you have to prove that they have inverses. So HK multiplied then taken inverse is going to give you the multiplication of the two inverses of K and H. Right? So this is going to be in KH. And this shows that they are closed under inverses, and thus what this means is that HK is a subgroup of G. Right? Nothing really much in this. The last one says that the isomorphism. Okay, so this is pretty much just combining all this, but the surjectivity part is kind of interesting. Okay. So yeah, F is going to be an isomorphism if and only if the two things are going to commute, right? H, K, the elements from H and K subgroups are going to commute, right? So what you try to do is you try to multiply these things. So H, K, H inverse times K inverse. Right, so you try to multiply the conjugates. So H inverse is the conjugate of K with G, and this one is just like putting the parentheses at the in the other side, right? And they are still the same. But this one on the left hand side is going to be in K because K is normal, so the conjugates are in K, and the right hand side is in H, because the right hand side is the conjugate of something in H, right? So it's going to be, because H is normal as well as a subgroup, so it's going to contain that. But since the the intersection of H and K is just the identity, so this thing has to be equal to the identity. So HK times H inverse K inverse is equal to the identity, thus making them commutative. Alright, so this shows if F is both injective and surjective, it is commutative, thus making the subgroups normal, right? Okay, so that was that.
This is a place where I kind of wish we were in one of those other books with lots of examples, so that I know that he's about to give one example about groups of order 4. It's not obvious to me. You can probably give tons of interesting examples, and I feel like I'm not quite getting it. I guess a non-example of this would be to look at S3 and look at the subgroup of order 3 and one of the subgroups of order 2. Almost all the conditions here are satisfied. The only point of intersection would be 1. I think that every element of G of S3 can be written the product of something in each of those two subgroups. Subgroup of order 3 is normal, but it's the subgroup of order 2 which is not. Otherwise, you would be able to say that S3 was equal to the direct product of those two subgroups, which is definitely not true, because the direct product is abelian and S3 is not.
Yes.
I wonder if there are some non-abelian examples that are interesting other than just saying like Z21 is Z3 cross Z7. I guess I need to look in another book to see if I can see another interesting example.
That would be interesting, yeah, because I don't know. Did you find Artin to be dry? Many people complain Artin to be dry.
I get alright.
Yeah.
I
Sometimes.
guess I don't have complaints, except for right here I could use another example.
Yeah, some people have told me like Artin writes in the Bourbaki style. Well, I have to disagree. Maybe they haven't checked Bourbaki, that's why they haven't seen the page.
With you on that. I'm not in love with Olufi, but I will say that he has more personality in his writing.
Yeah, I mean the thing is he's more general and he's like categorical, but it's like you don't feel the dryness right out of the bat.
Great.
Right, Balto says Herstein has examples. You're saying Herstein's topics in algebra, right? That should be it.
That's probably a really good place to look. That was my first algebra book, so that'll be where I check next.
Let's see. Was that in undergrad? I mean, it's often used in undergrad. I know.
It was back in the day. I don't know what's popular now.
Okay, now Artin is popular.
Okay.
Okay. The standard book, the standard book then is, what was that? Abstract Algebra. I think that was for undergrad students or something like that. Not sure.
Christine really did have great problem sets, though. I mean, graded from really straightforward problems to really challenging ones, so it's a good source for that.
Okay, that's nice. I haven't checked the problems for sure. I have checked like some chapters, some sections. I refer to Herstein, but not the problems. Okay.
I didn't find it a very good source for linear algebra, though. At least at the time, the stuff on canonical forms was hard to follow.
Okay. Yeah, he directly starts from like set theory though. Yeah. Artin starts from matrices. Yeah. But yeah. Yeah, either way, this Klein 4 group example, let's see. So there are two isomorphism classes of groups of order 4. The class of the cyclic group C4, and the class of the Klein 4 group, which is isomorphic to the product of the cyclic group of order 2 with itself. Okay, so yeah, so you have a little proof here. You have a group of order 4. The order of any of these elements is going to divide 4, sure. And you have two cases to consider for this. Case 1 is when G is going to contain an element of order 4, right? So then you're going to have like the whole group G would just be a cyclic group of order 4. The case 2 is when every element of G except the identity has order 2. Okay, so yeah, in case 2, you're going to have the inverses are going to be the elements themselves. So if you take two elements, then xi has order 2, xy has order 2. So the product of xy with its inverse is going to be the identity. This shows that x and y commute, and they do. And since okay, so thus the whole group is abelian. Thus every subgroup is normal because the group is abelian. We choose distinct elements from the group, and we take the subgroups to be the cyclic groups of order 2. So H and K are generated by X and Y and have order 2. Then by the propositions, the last option of the proposition, last claim of the proposition says that this group is isomorphic to the product of the groups generated by X and Y. So that's pretty neat, but yeah, not enough examples. Wait. Hmm. Okay, so I was looking through this book, but with the hope for some examples, but it turned out to be more dry. This is Hungerford, and well, it's the same kind of theme. Yeah, definition, theorem, proposition, proof.
It's not quite as comic as Bourbaki, but it also really goes back to, it doesn't start off with groups. It starts with things that are just shy of being groups,
Monoids and groupoids.
like magmas. It doesn't go all the way back to magmas, but so I got distracted. Where are we?
Yeah, so we're just about to start quotient groups.
Awesome.
Yep, quotient groups and a few lemmas. I think like we're going to see more of quotient groups when we do the second time group theory. But yeah. Yeah, I think, I mean, like, there's no doubt we're leaving a lot of group theory behind. We're not even touching. That would be, what was that? I mean, there are some sophisticated theorems, but, well, again, you can't really do everything. But, yeah, I think, like, as much we've done and we'll do group theory, it's enough for us to, get to modules and fields and stuff. Hmm.
When you were doing algebraic topology, didn't you sometimes abelianize the fundamental group by taking the quotient by the commutator subgroup or something, just to make it easier to classify? So
Yeah,
I don't think that we can avoid quotient groups. I think that this
yeah,
one's pretty important.
it is. It is. In algebra topology, if you can make something abelian, it kind of is. It kind of does a wonder. You know, you like some things just get a lot more simplified, and the fundamental group is much more neater. Um, especially
There are
just
classification
yeah,
theorems for abelian groups. So
yeah, right. Wait, that's wait. Let me see my schedule. Um, I should
coming up,
remember. I should remember most of my schedule, but what was that? CSV. So we are supposed to do the basis theorem and the fundamental theorem of abelian groups on our mole group theory
There it
weeks.
is, week 11,
Yeah.
lesson 11.
Yep.
Coming up soon.
Yeah, not too bad. We'll be doing that from Rotman, so yeah, he's much better. And of course, the important theorems, the Sewell theorem and the Jordan-Holder theorem. Yeah, we can't leave that. Okay, anyways, let's get the quotient groups done. I just found this thing kind of interesting about the cycle groups. Let me post this. This was from Rotman's Introduction to Group Theory. There's this like a very nice table where you have the permutations and the parity and the cycle structure and whatnot. Is there a reason we do rings before we do the advanced groups? It's because well, there's no specific reason. It's just that I didn't want to keep rings too. I mean, the thing is, I kind of believe that we should do rings first and then groups. But as we're doing a lot of group theory already, so I think we can spend 2 weeks on ring theory because getting back to advanced stuff. Because if you think about it, I think rings make more sense without groups, doesn't it? So yeah, this was from Rotman's. He has the C1, C2 to C11.
I don't think it's unheard of to do rings before groups because folks who are meeting it for the first time already know some rings. They're familiar with the integers and the rational numbers. As abstract groups are unfamiliar. They don't have as many good examples or interesting examples.
Yeah, I think there was this professor, and he used to say that the best way to do abstract algebra is like bring up linear algebra as soon as you can, because that's where like students have the most intuition about, and like it's something that they've encountered already in a very concrete sense. So if you can like build up from there, but it's hard to build up from linear algebra because like vector spaces, like unless you have like rings and modules at least, you can't really build up direct vector spaces. So yeah. Regardless, let's just finish this quotient groups part and we'll be done. Okay, so we'll show that a law of composition, we can define it on the set of cosets of a normal subgroup of any group. So you can make, so what you do is you have the set of cosets of a normal subgroup, and then you turn that into a group, and that will be the quotient group, right? Okay. So yeah, when you add congruence, like when we were doing like some arithmetic theory, you have A congruent to B mod n, then C congruent to D mod n, then you can add them, and then you can they're going to have the same congruence class for this modulo n. So that's somewhat like creating this kind of quotient construction. So yeah, they also give the examples of angles, right? So every real number represents an angle, and two real numbers represent the same angle if they differ by an integer multiple of 2 pi, right? So you can have the group n of integer multiples of 2 pi, so that will be 2 pi k, is going to be a subgroup of the additive group of additive group of real numbers with the addition, and the angles would correspond to the cosets theta plus n of the integer multiples in the group, right? So the group numbers, so the group of angles is the quotient group whose elements are the cosets. That's the idea, right? You have the cosets of a normal subgroup and you make it into a group, and you have the quotient. Okay, so let's see. So the set of cosets of a normal subgroup of n, the normal subgroup n of a group G, is often denoted by G slash n, so G over n is going to be the set of cosets of n in G. So when you regard a coset C as an element of this set, you have the equivalence classes. You can put the closed brackets around it, and if C is specifically this coset an, then you can use the bar notation to denote the element C by a bar. So a bar means the coset an, right, of the subgroup, normal subgroup n. And then what you can do is you can denote the set of cosets by G bar. So G bar denotes the set of cosets. I kind of sense that some problems in the P set have a bit of inconsistency with the notation. Nonetheless, I've mentioned the books, so you can check the notation there. But I believe most of them are consistent. So yeah, we have the theorem which says that you have a normal subgroup, then you have the quotient, with the set of cosets G bar. Then you have the law of composition on G bar, which makes the set into a group such that the map phi going from G to G bar, which is defined as taking every element of G to a coset in G bar, is going to be a surjective homomorphism whose kernel is M. Right? So this is kind of important. So this set of cosets, it has a law of composition, and you have the map going from G to G bar, taking every A to a coset generated by A, and this map is a surjective homomorphism, and the kernel of this map is the normal subgroup of the group G. Okay. And this map is called the canonical map from G to G bar. Right? So the word canonical just indicates that this is the only map that we might reasonably be talking about when we say that we are taking an element to its coset. Right? So it's the fundamentally only map that we can construct with this information. Okay, so you have a corollary of this theorem. The theorem is just stating that this is a map and it's subjective and whatnot. But the corollary is that if you have the canonical homomorphism, then you have A1 till AK are elements of G, then the product of these elements is in the normal subgroup, right? Okay, so if the product is in the normal subgroup, then the product of the cosets generated by these elements is going to be the coset generated by 1. Wait. Right, so if you represent this whole product with P, so this is the proof, then P is going to be in N, right? So then if you apply the canonical map onto P, you'll get P bar, and P bar okay. So yeah, P bar is the identity, right? But since pi is a homomorphism, you can just say that the product of like this bar that is applied on this whole P, which is the product, you can apply it individually to each element A1 till AK, and you'll get the bar P bar. Okay. Okay, so to make this set of cosets G bar into group, you have to have this law of composition. Then you have to make the law into a group, so that must satisfy all the group conditions. Then pi is surjective, you have to prove that. Then you have to show that the kernel of pi is the normal subgroup. Okay. Yeah, so this is just a notation that if you have two subsets of a group, then like A, B denotes the set of products of the elements from A and B, right? So this is the product set. So you're going to have this lemma, right, and a few other lemmas before we verify the conditions necessary for this G bar to be a group, right? So yeah, so you have the normal subgroup, then you have AN and BN are the cosets of N. Then the product set from this AN and BN is also going to be a coset that is equal to the coset of ABN. And this is pretty much straightforward because AN and BN, the product set is just going to be the elements, the product of the elements from the given cosets, right? And thus, like, yeah, thus, you can like, oh wait, because you have the normal subgroup, your left and right cosets are all equal, so you can like manipulate the things from left and right. So A and B and multiplication can be written as A and B times N. So then you can like again NB can be written as BN. This will be AB NN, and NN is just N because it's subgroup, so it becomes ABN, right? So, and that's what we need. So thus the product set of two cosets is also a coset, and that is equal to the coset of ABN. It is the product of the elements that generate the cosets. And this lemma, what it does, it allows to define a kind of multiplication on the set of cosets, right? So the set of cosets contains cosets. You want a way to multiply these cosets, and you have this. So so how you do this, you have C1 and C2 are two cosets, then you represent them with this bracket notation. So C1, C2 is equal to C1, C2 within brackets. So C1, C2 is the product set, and then you're taking, then you're considering the coset of the product set, right? So yeah, so the lemma shows that this product set is another coset. So to compute the product, it's pretty much the same thing from the lemma again. You take an element from C1 and C2, then C1 would be AN and C2 would be BN. Then C1, C2 is the coset ABN that contains AB, the product AB, right? So you have the naturally the formula, right? So yeah, and then you can include the canonical map into all this by saying that the product pi of A, pi of B is equal to just pi of AB, because the products work very smoothly with the cosets by our definition, of course. So lemma 2.12.8. So this lemma would you would have a group and you have a set Y with law of composition, and both the laws in both the things, the group and the set, you have the multiplicative notation. So phi is something that goes from G to Y, is a surjective map, has the homomorphism property, but it is not an homomorphism because Y is not a group. So it works like a homomorphism. So the products respect the multiplication. So phi of AB is equal to phi of A times phi of B. Then now Y is a group and phi is a homomorphism. So this is just a way of trying to prove that Y is actually a group, and thus here Y is going to be replaced with G bar, of course. Okay, so because phi is surjective, the group structure you have for G gets carried over to Y, right? Because it works like a homomorphism. Right? So the associative law is that if you take three elements of Y, since phi is surjective, Y any element Y I Y with any index, you can write it as the image for some element in G, right? So how that helps is like you can take the product of y1 and y2 and then take the product of y3, and that would be equal to just taking the product of phi of x1 with phi of x2, but then taking phi of x3, but phi of x1 times phi of x2 is just phi of x1 x2. You do that, and then you include again phi of x1 x2 then x3, and because the because we have G as a group and x1 x2 x3 are all elements in groups, so this thing within phi can be you can apply associativity on that. So you get phi of x1 then x2 x3, and then you again take them all out and you'll get phi of x1, phi of x2, phi of x3, and thus you'll get y1 within brackets y2 y3, and thus making things associative in Y, right? Thus the group structure gets transformed. Right? Thus, the canonical map is the phi here, right? So the phi is analogous to the canonical map, and thus transforming the group structure from G to G bar, right? So the only thing that's left is making sure the kernel of the canonical map is going to be the normal subgroup. Right, so what you want is that you want the elements which, when mapped with the canonical map, give you the identity. So pi of A is equal to pi of 1 if and only if the code set generated by A is equal to the code set generated by the identity, so that is AN is equal to 1N. And this is going to be true if and only if A is going to be an element of N, right? Otherwise you can't have like AN equals to 1N, so that's just going to be N. So A has to be the element of N, thus making that the set of elements that get mapped to the identity are all in N. Thus, the normal group is the kernel of the canonical map. Right, this diagram that they have, the schematic diagram of quotient multiplication, this is kind of interesting. So you have like this B point here, and this kind of, I don't know what this is. This area shaded is Bn, so this is the coset generated by B, and then on the upper side you have A, and the coset generated by A, that is An, and then when you multiply these two, you're going to get the coset ABN, and the elements there are going to be AB. Okay, so the coset is generated by AB, the product of the two elements. And that was about how the quotient group is well defined, and the canonical map and its properties. Okay. So we have we have, first of all, okay, so I think they mentioned just the proof for the first isomorphism theorem, but not the second and third, because I think, yeah, Artin has like another chapter on groups, right? Yeah.
Pretty sure that the third isomorphism theorem is problem 8 on this week's homework.
I know that.
Problem that you pulled from McLean.
Yeah, this was interesting, but the thing is, the McLean, this problem, I was intrigued because he put this as a normal problem, but if you look at Serge Lang's book, he like gives this emphasis as like a theorem and important theorem, but yeah, McLean doesn't talk about that.
And here it says it's less important. There are also theorems called the second and third, but they're not as important.
Okay, so yeah, we just have the first isomorphism theorem, and the proof is well, the proof is pretty straightforward, but the corollary seems to be interesting. Okay, so the first isomorphism theorem says that you have the surjective group homomorphism from G to G prime, and it has a kernel N. Then the quotient group G bar generated by these set of cosets, whatever, equals to G or over N, is isomorphic to the image G prime, right? So to be precise, the canonical map going from G to G bar, so there is a unique homomorphism phi bar going in the opposite direction such that the whole thing commutes, right? So yeah, makes sense. You have phi going from G to G prime, pi going from G to G bar, and you have phi bar going from G bar to G prime. So you can write phi as phi bar composition pi, and you have to show that there is just a unique way to do this. So and it kind of makes sense because by definition G bar contains cosets of n, and cosets are fibers of the map phi, right? They're preimages. The map phi bar is the one that sends a fiber to its image in G prime, right? So phi bar is going to take an x bar, so that is a fiber, and it maps it onto phi of x, right? Phi of x again is the image of x from the group G, right? So for any surjective map from G to G prime, one can form this set G bar of fibers, and then one obtains a diagram as above. Yeah, you can, like, because this phi bar sends a non-empty fiber every time, you can make a set of those fibers, and that will be G bar. So in which phi bar is going to be the bijective map that always sends this fiber to its image, right? And this is because the group homomorphism that we have is actually surjective, right? So it works out. But if like the phi is a group homomorphism, phi bar is an isomorphism. Right. Okay, right. So just above this line, they were talking just in terms of sets. So if phi is just from set G to G prime without any group structure, you can still have the set of fibers that is G bar, right? And thus phi bar there is just going to be the bijective map between the sets. But when phi is going from groups to groups, that is, it's a group homomorphism, then the phi bar is going to be an isomorphism, right? And
Part of the big thing there is that it's now an isomorphism because it's 1-to-1.
yep.
Phi might have been many to one, modding out by the kernel. The resulting map is going to be 1-to-1.
Yeah, but I think like here they kind of like transfer the one-to-one because they just said that it is bijective in terms of sets, so it's going to be isomorphic in terms of groups. Yeah. Okay, so the corollary is that phi goes from G to G prime is a group homomorphism, kernel N, and it has an image H prime. So the quotient group is going to be isomorphic to the image, and that makes sense. because the image that you're going to have, you're going to, this phi bar is going to be the isomorphism from this G bar to the image directly, and thus making it isomorphic.
Probably not an exact analogy, but that kind of has the feeling of the nullity theorem from linear algebra, right?
Yeah.
The dimension of the image plus the dimension of the kernel equals the dimension of the domain.
Indeed. Yeah, I think like this problem 9 from Bourbaki is kind of looks something that we can do with this maybe. I'm not sure because like in that section Bourbaki hasn't a whole, I'm not sure, I haven't gone through all the stuff, but I guess he hasn't given the first isomorphism theorem. But yeah, so that is done. Artin says that second and third isomorphism theorems are not important. We have to take his word, and I'm not sure they're not important, but like I don't know, for some reason Artin doesn't like it, I guess. Okay, so that was a group theory. You have the preset until next Wednesday.
So before we break, there are a couple of tiny typos on the problem set. Do you have it handy?
Yep. Can fix them. So where are?
So there's only one which is important, and that's in problem 2.
G1, G2, or the product. So the product group G. Wait.
Get there.
Oh, okay.
Be G sub 1 cross G sub 2.
Yeah. So I think I've made like instead of underscore it was hyphen. Let me fix that.
Everybody would guess the correct thing on that. The other two are not as important. But problem 1 references Artin exercise 11.9 at 11.8.
Oh, that's a big mistake. Okay.
In problem number 9, the Bourbaki problem.
Yep.
It's actually section 4, exercise 6.
Is it section 4, the groups? Oh.
But the statement is perfect. So
okay.
Nothing of consequence this week.
So let me fix the LaTeX.
Really appreciate your picking out these problem sets. So far they've been awesome. Definitely some challenging ones each time.
Good to know. So this is section 4, and that one was Artin section, sorry, problem 9, okay. Yeah, okay, so next will be rings. I kind of feel like we're going to go through rings in a rush because we're actually going to go through a lot of things, but we'll see. If things don't go as nicely, we can actually extend another week just to catch up everything. So it's not really a big deal, but yeah, I'm more excited about rings when they get commutative.
That's what I was going to say. Whatever we miss in rings in the next couple of weeks, we're going to be forced to come back to when we do commutative algebra.
Yeah. That's because the thing is, the book that we're going to use, what was that? Atia. He does review a lot of ring theory already.
So, and it's mostly just problems, so I'd have to do that more seminar style, because we're not going to be able to just flip through the book.
Yep.
I'd have to, problem sets will be just whatever problems from the book we're going to do and sharing our work.
Mm-hmm.
That's weeks away.
Yeah, that's like, that's far more, farther than the rings that we have now, so, yeah. I think, like, the course doesn't, do much of, like, just not fair towards, field theory, Galois theory. I mean, we're going to do enough of Galois theory and field theory, but not much. So, no, we'll see.
Really interested in learning that well.
Mm-hmm.
I don't think that not knowing it is going to hold us back from much other stuff.
Okay.
Could be wrong.
Yeah, okay, so that's nice. So this is going to be the end of like July, right? So before July ends, we can do a review session for group theory, right? So that will be like, I mean, we would have started ring theory, but we could do that anyways. Okay, so see ya next Tuesday. We'll do rings, and yeah, have a good day.
Thanks a lot. See you next time.